We're going to look at two examples of doing calculations with torque on a current loop. Sorry, no examples with charge to mass ratio. The homework problems you have with that are pretty simple and straightforward. So moving right along, we've got a circular coil of a given diameter. It's 10 loops. We know the current and we know the external magnetic field. We want to find the maximum and minimum torque acting on the loop. So we're going to use our brand new torque equation, NIAB sine theta. Now the maximum value occurs when sine theta is equal to 1, and the minimum when sine theta is equal to 0. So the minimum torque is going to be 0. There we go, that part's nice and easy. The maximum torque is when that is 1, as I just mentioned. So this is not all that much more difficult than the first part. We're just plugging in numbers. We have the number of loops here, we've got the current. Now the area, when we derived this formula, was for the area of a square, but it actually holds true for the area of any shape of coil. It would have just been more complicated to derive it with another shape. So we can go ahead and do the area of a circle, which is pi times the radius squared. Now this is the diameter, and we also want to convert it to meters, so we're going to make that 0.1 squared. Put all that in parentheses just to show you that's the area. And then we've got the 2 Tesla magnetic field. Multiply all of that and we get a torque of 1.88 meter newtons. Okay, one more example. Here we've got 15 loops, we've got a coil in the XY plane, and here it's uglier because our magnetic field is defined as a vector in 3 dimensions. And we want to find the magnetic moment of the coil for part A. That part is not too tricky. We just need to do NIA. And we've got N is 15. We've got the current is 7.6. And then the area, again, is the area of a circle. So we've got pi times 0.22 centimeters over 0.22 meters. And all of that is squared. Now because this is in the XY plane and so the current is clockwise, you would imagine looking down on this loop and having the current go clockwise. So if we use our right hand rule where we curl our fingers around the loop, this magnetic field is going to be heading into the ground or into the page, whatever you want to say. So this is going to be in the negative K direction. So all of this works out to be negative 4.33 in the K direction, and the units on this are going to be amps times meters squared. So there we go, part A. Part B, we need to find the torque, and we're actually going to use the full nasty cross product because we have everything defined component-wise. And if you don't remember, the cross product is the determinant of this matrix, which works out to be this big nice thing here. In our case though, since mu, the magnetic dipole moment, only has a K component, then the only parts we need to worry about are the ones where we have AZ. So we need this guy here, and then we need this guy here, which is in the J direction, but not including that thing. Okay, so we can go ahead and write this out. It's going to be negative mu z times by, the I hat direction, plus mu z bx in the j hat direction. We can go ahead and plug in some numbers. That's going to be a negative out front, and then we've got a negative 4.33 for our magnetic dipole moment times 0.6. All of that is in the I hat direction, plus negative 4.33 times 0.55, and that is in the j hat direction. So this works out to be 2.6 I hat minus 2.4 j hat, and these will have units of meter newtons. Okay, that wasn't as bad as it looked at the start. Part C, we want to find the potential energy. And we can use, again, the vector expression where we've got negative mu dot b. This actually works out to be quite nice. You could, I mean, if we wanted to use mu b cosine theta, that would actually be harder to figure out the angle between these two things. If we just use the dot product, and remember that you are taking the component of b that is in the direction of mu. So that means all we have to worry about is the k component, because mu is only in the k direction, right? So this works out to be nice and simple. We've got the negative signs cancel out because there was a negative there and a negative there. So 4.33, well, those two cancel out. There's another negative sign here on our k component of our magnetic field, so 0.65, that's being multiplied, and we end up with negative 2.8 joules of potential energy. Okay, see you next time.